Hi, welcome to the next lecture. So today the question that I have for you is consider the De Morgan's law stated below. So I guess you need to recall on the De Morgan's law here. What is De Morgan's law? If you have A and B two sets coming from some universal set, so A, B, they are subset of some universal set X. The union of AB and its complement. If you take the union and take its complement, that will be equal to the complement of intersection. So as stated here, A union B complement is equal to A complement intersection B complement. It's something that you can even visualize on Venn diagram. So suppose this is A and B. A, B. A union B would essentially be everything, right? That is covered. Within these two circles, everything that is covered is A union B, right? Now, what is the complement of that? Everything that is outside is the complement. What are we talking about? We're equating it to A complement union B complement. Now, what is A complement intersection B complement? So what is A complement? Everything that is not in A. What is B complement? Everything that is not in B. So it's going to be everything here and here. Outside, of course. So what is the intersection of these two? Yellow and green. What is the intersection that you can see? So except for this entire thing, everything else it consists of, which is same as the complement of A union B. So the statement that you have here is absolutely true. This is a general case that I've created. You create any kind of Venn diagram, you will get that this statement is always true. And so will be the other statement, which I leave for you because our question starts now. So this is for two sets, A and B. In case you have two sets, A and B, the complement of A union B is equal to A complement intersection B complement. And number two, the complement of intersection of A and B is equal to A complement union B complement. Now we have to prove the following. Today, what we have to prove is that the complement of union of any family of sets equals the intersection of all the complements. And number two, the complement of the intersection of, again, any family of sets equals the union of all the complements. This basically, the two statements that I've given to you, it's an extension of the two set case that I've just revised with you. How? The first thing that you need to understand is what is any family? How we define family of sets. So when you say any family of sets, it could be finite family or it could be infinite family. So you don't know whether you should be taking n number of sets in this family, A1, A2. Maybe yes, maybe it could be arbitrary, A alpha, A beta. You don't know where to stop, okay? So what we can say is that let AI, where I is some index. This I, capital I, does not stand for integers, okay? It is any index. Because we don't know whether it's finite, infinite. So any index it is, okay? We don't know whether we just have to take n number of sets here. Or there could be whatever number of sets here. But anything that falls here, if you say A1 belongs to this, that means it's a part of this family. If you say A alpha belongs to this, that means A alpha is a part of this family. Now, being a part of this family might involve some property. We don't have to do that because we are taking a general case. What are we trying to say here is that Statement 1 is talking about complement of the union of any family of sets. So what is the union of any family of sets? You're talking about, say, A1 union, A2 union, A alpha union, so on and so forth, everything going on. Union of any family of sets. So taking the union of whatever members in this family are. This is denoted as a big union outside, A, I, because we are giving it I as the subscript, where I belongs to this index I, whatever is this index, finite or infinite, okay? Union AI, where I belongs to capital I. This means you are taking union of all the sets that are part of this family, okay? Now, that's number 1. Now, what are we saying in part B? We are saying the complement of intersection of any family of sets. So I want to define, what have I done? I've defined union of any family of sets. Now I want to define intersection of any family of sets, first of all for you, and then we move on to the proof. This is, guys, union of any family of sets. It would be defined or denoted like this. Okay. Similarly, you can denote the intersection. Intersection would be a big intersection outside, AI again, where I belongs to the index capital I. So this is required for A and this is required for B. Okay. Now let's talk about this question. A part means the complement of union of any family of sets equals the intersection of all complements. So it basically means that you take the union AI, I belongs to capital I. You take the complement of it. You take the complement of union of any family of sets. It equals the intersection of all complements. So intersection of all complements, let me probably write that down separately for you. Intersection of all complements. If you just have 2 sets, in case of 2 sets, it is A1 complement intersection A2 complement. In case there are many more, then it keeps on going, right? So it keeps on going and it becomes a big intersection outside AI complement, because you're talking about intersection of complements, where I belongs to capital I, because we don't know the index. We don't know whether we have to go only up till N or something else. Okay, we don't know the index here. So this is what intersection of all complements would mean. So again, this is required for A. And for B, it's required union of all complements. You need to understand what will be union of all complements. Union of all complements. This is something that you will require for B. So what will be union of all complements? If you have 2 sets, the union of all of complements would be A1 complement union A2 complement. If there are many more and you don't know the count, it becomes a big union outside AI, where I belongs to the index I, which you don't know what exactly it would be, finite, infinite, anything. Now we can state what we have here. Once we have this knowledge of what to denote and how to denote these, now you can actually write down in terms of what you have to prove. You have to prove in A that the complement of union, which is union AI, whole thing complement, it is equal to the intersection of all complements, that it is equal to intersection AI complement where I belongs to capital I. And on the other hand, for B, what do you have to prove? Basically, the statement means the complement of intersection of any family of sets. So you take the intersection of any family of sets and you take its complement, that should be equal to union of all complements. That should be equal to union AI complement where I goes, I takes all the, I takes care of all the sets that are there in this family. Okay. This is what we have to prove. Let's start with part A. First of all, state what you have to prove. Again, we have to prove in A that union I goes, whatever the index is, the whole complement is equal to intersection AI complement I belongs to the capital I, which stands for your index. Let's make use of elementary set theory here and prove it. So let there be some element, say A, which belongs to union AI, I belongs to capital I complement. Now, when is this possible? Okay, another thing that I want to put up here is that whenever you have to prove equality in sets, equality in set means double containment, right? And I've talked about that when I did set theory with you guys. Double containment, right? Double containment in other sense stands for if and only if, because you will have to prove both way implications. Again, I've spoken about that in my previous lectures. So A belongs to your left hand side, which is union AI whole complement. That is only possible if and only if. It's possible if and only if A does not belong to union AI, right? A in case does not belong to union AI. That means A is not in any of the AIs, right? A is not in any of the set from this family. This is only possible when A does not belong to AI for every I belonging to capital I. For every set in this family, element A cannot be in that set. Okay? If that's the case, if A does not belong to any AI from this family, that means A belongs to AI complement for every I belonging to I. That means AI is in the complement. It's not in any AI. So it's in the complements of AIs, right? Now, if A is in the complements, if it is in some sets, and for every set it is there, that essentially means that it is in the intersection of all the sets that you will take up. Because it is happening for every I in this index. Element A is in AI complement for every I in this family. So that means it is in the complement set for every I, okay? So it is in the intersection. And well, isn't that your right-hand side? That's what you wanted to prove here. You start with an element here. You start with an element here and you prove that that element is here with if and only if. So if basically, what is the importance of if and only if? I'm going to tell you here. When I've used if and only if, that essentially means I have done this part. Your left-hand side is contained in the right-hand side, because for that, I need to tell that in your left-hand side, is also in the right-hand side. This is what you have to prove. And the right-hand side is contained in the left-hand side, means that I would start with an element in the right-hand side, and that would imply that that is in the left-hand side as well. So what does this mean essentially with if and only if? I've done both the things. I've gone from left to right and right to left, and at one go. Okay. So that's the answer to the first one. It's all about notations. Once you are clear with the notations, it would be very easy. And that's why my thrust was first to tell you what any family of set would mean, and then to move on to the unions and intersections, how you denote it. The next one is the complement of intersection of any family of sets equals the union of all complements. So we have to prove that means the intersection AI whole complement, where I belongs to capital I, is equal to intersection AI, not intersection, it is equal to union AI complement I belongs to capital I. Okay? So how to go about it? Again, it's equality. So you require double containment. Double containment requires left-hand side is a subset of right-hand side. Right-hand side is a subset of left-hand side. That means you will pick up an element here, and that should imply that that element is here. And on the next go, you pick up an element here, and that should imply that element is here. What I'm going to do is I'm going to use if and only if. Because if you combine the two, that means you want to actually prove if and only if. So let's do that. So if and only if. Let me take an element A, which belongs to the intersection AI complement. This is only possible if and only if A does not belong to intersection AI, where I belongs to capital I, that is intersection of all the sets in this family, right? Now, if that's the case, that means think in terms of just two sets. This is critical. So, when do you think an element is not a part of intersection of two sets? In case it's a part of one set but not the other set, or it's not a part of both the sets, right? Or either it's not a part of one of them, then it's not in the intersection. So that means when we say that A does not belong to intersection AI, that should be the case if and only if A is, at the least, it is not a part of one of them, at the least. So A is not a part of AI for some I belonging to I. So the language changes here. It's not for all anymore, for some I. Because see, try to understand, X is not a part of A1 intersection A2 in case it's not a part of, if to be in the intersection, you have to be in both. If you are just in one but not in the other, then you're not a part of the intersection, right? So that's what we want to say here, that if you're a part of some but not others, then you're not a part of intersection. So this would mean that A is not an element of some of the members of this family of sets, okay? So which means that A would belong to, or let me just make it AJ for you. Let's say some J, let's say distinguish it from I was taking I for every, so I am taking a particular one, say J. So that means A would belong to AJ complement. AJ complement. Now, if it is in one set, if an element is in one set, it's always in the union, right? Whether the set is complement or not, it doesn't matter. So if it is in one set, it is always in the union. So that means if A is in, say, at the least in one set, AJ complement, it will be in the union of all the complements, and that could be written as union AI complements. I belongs to capital I. If it's in one, it's in the union. And that's what we wanted to prove. If you see your right hand side, that's what is your right hand side. The key here is that you need to understand when is an element not in intersection. When it is in one, perhaps not in the other. So at the least, it will be in one, but not others. That's the case that you have to see, and it's easy to prove it. Thank you.